This tutorial shows you how to work with rasters in the Geographic Information system known as GRASS GIS. For more information on GIS, and on GRASS GIS in particular, see the links in the show notes below. I also have a video with more background about rasters. You can find it in the show notes as well. This tutorial assumes that you have GRASS GIS installed. Instructions can be found in the show notes below. This tutorial assumes you are using Ubuntu Linux version 20.04 as your operating system. If you do not have Linux, you can emulate it on your Windows or Mac computer for free. See the show notes for details. In fact, I am emulating Linux right now on my Mac computer using VirtualBox. I have a VirtualBox virtual machine pre-configured with the software I will show you today, as well as other population genetics and ecological niche modeling and GIS software. See the show notes below for step-by-step instructions to download and hook up this virtual machine within your Windows or Mac computer. But before I can get into that, I need to tell you a little bit of background about rasters. I have a whole video separate from this one about rasters that you can watch, and you can see the show notes to find the link to it. But rasters are so strange that to understand what we're going to be doing today requires me to spend a few minutes going over what exactly they are. There are two different types of GIS data, broadly speaking. There's vector data, which is in the form of points, lines, and shapes, called polygons. And then there's raster data, where instead of the data being stored in the form of points, like the locations of fire hydrants, and instead of the data being stored as lines, for example, highways, and instead of the data being stored as polygons, shapes, for instance, the property boundaries of someone's ranch, the data in the raster format is stored in a grid, where every grid has an attribute. And you can use that attribute to tell you about what is happening in that grid. So let's say that in the real world we had a lake and several picnic tables next to the lake. Let's say that these are picnic tables. In raster format, we could represent this data as we take the same spatial extent and we divide the spatial extent up into squares. The squares that do not have the lake are coded as a 1. The squares that do have a lake are coded as a 2. The squares that have a picnic table are coded as a 3. Now you can see that this particular raster does a bad job of representing what is happening in the actual landscape. But that has to do with the very coarse resolution of this raster image. If we divide up this raster image into smaller grid cells, then we could more precisely define the area within the landscape where the lake occurs and the areas within the landscape where the picnic tables occur and where they do not occur. Raster images are all over the place in our everyday lives. For instance, images that you take with a digital camera are stored as rasters. When you visit websites on the internet, the images are rasters. And if you zoom in on an image far enough, you'll find out that the nice smooth image that you're looking at is actually made up of jagged edges because the image is actually made up of little grid cells. And each grid cell has one single individual color to it. And so that the shadowing that you see is because of little grid cells that have other colors that are next to it. But at a fine enough scale, the images that you're watching on your computer are all rasters. Television screens are made up of rasters, and these are showing you different types of television screens. There is CRT television, which is the old time from when I was younger, And then here is the modern televisions using LCD, but they all have these pixels, which is just a way of dividing up the TV screen into a bunch of grids, and then every single grid cell has a single color. So while you see smooth continuous objects on your TV screen, if you zoomed in far enough, you would see that all of the images on your TV screen are actually very blocky because they're at a fundamental level made up of these individual little grids. There are going to be two attributes that will be very important to keep track of when you're working with rasters. Those two attributes are resolution and extent. When working with rasters in GRASS GIS, we're going to be setting the resolution. The resolution has to do with the size of our grid cells when we import rasters, work with rasters, or export rasters to another file. So if we use a fine-grained resolution, in other words, if we have small grid cells, then the raster images that we work with in GRASS will maintain a fine-grained resolution when we import them into GRASS and when we export them from GRASS to other file formats. However, if we use a coarser-grained resolution, in other words, if we have a larger sized grid cells, then the raster images that we work with in GRASS, either when we import those images into GRASS, or when we export those images from GRASS into another file format, or when we do different kinds of operations to those rasters, we'll end up making those rasters have a coarser resolution, as you can see in the image below. Because now the pixel sizes, or the grain sizes as they're often called, are much larger, so that the resolution of our image becomes a lot less detailed. It becomes a lot coarser. And again, that's governed by this feature that we're going to be setting when we use GRASS GIS. And this feature is called the resolution. And the resolution refers to the size of the grid cells that we're going to be setting as we work with these rasters, depending upon the desired result. If we want to make coarser images, which you may want to do if you want to have smaller file sizes, or if you want to have raster images that match other raster images that you have and that have a similarly coarse resolution, then you may want to use a coarser resolution for the GRASS environment. By the way, these raster images are still layers. So we still call them layers, but these layers are based upon rasters rather than based upon vectors. We can still overlay these layers on top of other layers and below other layers, including other vector layers. So we could show on a raster map or on a raster layer, we could still show the locations of fire hydrants, which are a points feature in the vector format. We could still show them in the context of the state of Texas. We could overlay those points on top of a raster image. The other thing to keep track of and to be very cognizant of and to set very specifically when you're using GRASS GIS with rasters is your spatial extent. You may have a raster image or raster layer that covers the entire world. But if you're only interested in the attributes of that raster for the state of Texas, you don't want to have an enormous file that covers the entire world. You don't want to be applying your analyses at the level of the entire world. You only want to be applying them at the level of Texas. You're going to want to define your spatial extent to be that of the state of Texas. And so you'll be often clipping your raster layers to a smaller size depending upon your area of interest. And when you make a clip, the way that it happens in a raster is always a rectangular shape or a square shape. So the areas outside of our interest within this rectangle that contains the shape of Texas, the areas outside of our interest are coded, those particular grid cells are coded with a special number that tells GRASS GIS to ignore those particular grid cells. And so in that way, we can have a raster that is clipped to the, within our resolution, exact shape of Texas. Rasters can come in a variety of file formats. They can be in a band interleaved by line format. They can be in a band interleaved by pixel format, band sequential. They can be part of a geodatabase file, or they can be in an ASCII grid format. And these are all formats that can be read by GRASS GIS and imported into a GRASS GIS database. This last one here, we will be, in addition to this .bil format above, we'll be interested in focusing on this ASCII grid format. This ASCII grid format is in many ways the most portable because it's the most simple. An ASCII grid format takes your grid, because that's what your raster is, and for every single grid cell in your grid, it's a text file which has the attribute of that particular grid cell. And then in the corner of this ASCII grid file, you have some other attributes about the raster, such as its overall size, the coordinates of the lower left corner, and the resolution of the raster. So this is a very simple portable file format, and this is the file format of raster data that's used for ecological niche modeling. You may have heard that term before, or species distribution modeling, where you can forecast the habitable places on the landscape for a species or community of interest. Ecological niche modeling is based upon raster layers. And the raster layers that are used in ecological niche modeling are in that format that I just described to you, that simple text-based format known as the ASCII grid. So we will be incorporating that into this tutorial as well. This is a quick splice to ask you to consider subscribing to my channel by hitting the subscribe button. It does not cost anything. It is totally free. But if you like what I am doing and want to support my work, I encourage you to visit patreon.com/joshbanta and make a voluntary contribution. The link is in the show notes below. Your support helps me to deliver new content and keep this channel current and vibrant. Thank you. Now let's go ahead and get started. The first thing you want to do is open up a web browser and navigate to my website. I have Google Chrome pinned here to the side, or if you're not using my virtual machine, you can search for it below, or search for the whichever web browser you would like to use. Click on Tutorials. When you come to my website and when you click on Tutorials, the website may look different. As of September, I'll be migrating to a different style. I'm going to use Control F to find what I need, and I'm going to type in GRASS. And I'm going to keep hitting Enter until I get to Tutorials for using GIS and the software GRASS GIS. Then I'm going to scroll down to Rasters and Raster Manipulation, and I'm going to click on Files Needed for Tutorial. Be careful, this is a similar looking tutorial down here. Don't click on these files. Click on the files for Rasters and Raster Manipulation. click on the download button. You can see that the download has completed below. You may exit out of Google Chrome. Navigate to your Downloads folder. I did this by opening up File Explorer, which I have pinned to my favorites here on the left, or which you can find by searching below. Go to Downloads. Double-click on rasterfiles.zip. .zip is an archived file format, and by double-clicking on it, we're running a piece of software that lets us look inside of that archived file folder. The next step is to go to your home directory, double-click on GRASS data, or if you do not have a folder in your home directory called GRASS data, you can create one by clicking on New Folder as I'm illustrating to you on your screen. In your GRASS data folder, create a new folder called Raster data. Then click Create. Double-click on that folder. And now, move it over to the side a little more. And now we're going to go back to our Archive Manager. I know this looks like File Explorer, but this is actually a different program. That's our Archive Manager. We need to get these files out of the Archive Manager or else we won't be able to use them. So I'm going to normal click on the first file. Then I'm going to go down to the bottom file. I'm not going to click anything yet. I'm going to hit the Shift key. Then I'm going to normal click again on the last file. Next, I'm going to come over here to the picture next to the file, and I'm going to regular click and hold it down, and I'm not going to let go. This is going to take all of those files and place them into the raster data folder in the GRASS data directory, and it will uncompress these files so that they are now accessible to us. Now I will close the Archive Manager software. Next, we're going to start up GRASS. You do that by opening up a terminal window, which I have pinned to my favorites here on the left, or you can search for below. With the terminal window open, simply type GRASS. We have to create a new GRASS location. For more information about how GRASS works, see my previous tutorial on GRASS using projections and transformations, which is the first in this series, and it goes into some more detail about using GRASS GIS and how it's set up with these GRASS locations. A link to that tutorial is in the show notes below. Click on New. Picking up from that last tutorial on projections and transformations, this GRASS location is the 8th one, so I'm going to call it Projection 8. Click on Next. We need to define the projection, ellipsoid, and datum of this GRASS location. We're going to do that by reading the information from a georeferenced data file. Click Next. Click Browse. Navigate to the GRASS data folder within your home directory. Double-click on Raster data. Select bio1.bil and click on Open. Click on Next. Now click on Finish. Click OK. Do you want to import this file, bio1.bil, to the newly created location? Yes. So we used this file to give us the projection, the ellipsoid, and the datum. And now we are also importing that file itself into the GRASS location that we are creating. Again, for more background on all of this, if this seems unfamiliar to you, you're going to want to see my tutorial on projections and transformations. Click OK. Click Start GRASS Session. We have imported our first raster. You don't see it in the table of contents here in the Layers tab, and you don't see it on the map because it's not yet being displayed, although it is there in the GRASS database in this GRASS location. To display it, we go to File, Map Display, Add Raster. From the drop-down menu, select Bio 1. Click OK. This is a really big raster. This is climatic data from the WorldClim database. This raster covers the entire world. If you're ever going to be working with this climatic data from WorldClim, always import the WorldClim data first before you import any of your other layers into that same GRASS location. Because GRASS has to set up a really, really big workspace within that GRASS location. And things will go haywire if you don't start with the WorldClim layers, which are going to have the largest spatial extent. Now we're going to add another raster from the WorldClim database. Go to File, Import Raster Data, Input of Common Raster Formats. Click on Browse. Navigate to the GRASS data folder within your home directory. Double-click on it. Click on Raster Data. And this time choose bio12.bil. For the output map, call it bio12. Click on Run. Now click on Close. Now we circle back to this idea of resolution. We are going to find out what the resolution is of our two raster layers. Are the layers high resolution or higher resolution, such as this image of Texas over here? Or are the raster layers low resolution with larger pixel sizes, such as the map of Texas or the layer of Texas over here? Let's start with bio12. If you are on a Windows machine, you will right-click. If you are on a Mac laptop, push down on the trackpad with 2 fingers and click on Metadata. Here's our resolution. The resolution for north-south is 5, and the resolution for east-west is 5. This allows for the pixels to be rectangular in shape rather than square in shape, so they can have a different length than width of the pixels. Notice the 0:05. This is a telltale sign that this layer is in the form of degrees, minutes, seconds. The first 0 here is degrees. The second 0 here and the third digit here are minutes. And if we saw another colon here followed by more numbers, that next set of numbers would be seconds. So the distances here for the WorldClim layers are given in degrees, minutes, seconds, where there are 60 seconds to a minute and 60 minutes to a degree. Going back to my lecture on projections and transformations and an introduction to GIS, which is also in the show notes below, on a spherical Earth, we create lines of longitude that encircle the Earth, and we create lines of latitude that encircle the Earth. So in this way, we can pinpoint any location on the Earth by a combination of the latitude coordinate, which one of these rings around the Earth, and the longitude coordinate, which one of the the rings that go between the two poles around the Earth. So we can specify an x or a latitude coordinate, and we can specify a longitude coordinate. But what if the place we're interested in does not lie exactly on one of these lines of latitude or exactly on one of these lines of longitude? Well, then you specify a fraction of this line of latitude and a fraction of this line of longitude. And these fractions are expressed as, at least in the case of this coordinate system that we're working with now, in the form of minutes. So every degree of longitude, which goes between, and a degree of longitude goes between these two bands of longitude. This degree of longitude here is divided up into a bunch of smaller lines called minutes. This degree of latitude here, in between this line of latitude and this line of latitude, is split up into 60 smaller bands of latitude. And those smaller bands of latitude are called minutes. So you've got minutes of longitude and minutes of latitude that help you better specify the location on the globe. Within each of those bands of latitude and within each of those bands of longitude, they're carved up into 60 even smaller bands called seconds, so that we can further and more precisely specify the location that we're showing on the globe. And so that's where you have the system of degrees, minutes, seconds. A degree of latitude specifies which one of these bands encircling the Earth we're referring to, and a degree of longitude refers to which one of these bands encircling the globe from north to south we're referring to. The minutes of latitude refer to these sub-bands in between the degrees of latitude and in between these degrees of longitude. And the seconds specify the sub-bands encircling the Earth in between the minutes of latitude and in between the minutes of longitude. So there's 60 seconds in a minute and there's 60 minutes in a degree. Now, for measuring distances, degrees, minutes, seconds is not great, because the distance in between two lines of latitude or in between two lines of longitude is going to be different depending upon whether you're at the equator or at the pole. So for instance, closer here to the equator, you can see that there's a big distance between these two lines of longitude, and that there's a big distance between these two lines of latitude. So the physical distance represented by a degree is roughly the same here, whether you're talking about the distance between two longitudinal bands and whether you're talking about the distance between two latitudinal bands. But degree means something very different if we're here near the North Pole or near the South Pole. So here, the distance between these two lines of longitude is pretty short. But the distance between these two lines of latitude is pretty long. So the distance in terms of a degree of latitude here is longer than the distance of a degree of longitude. So the units of degrees, minutes, seconds are not great for measuring distance or for making pixels, because the size of your pixels is going to be very distorted towards the north and the south poles, because while these pixels will be represented as squares of 1 degree by 1 degree, or in our case 5 minutes by 5 minutes, 5 minutes of latitude and 5 minutes of longitude, those things being represented as squares, forming these pixels for the more northern latitudes of the Earth, are actually more like the shape of triangles, or at least trapezoids. Whereas these pixels that are in the dimensions of 5 minutes by 5 minutes, closer towards the equator, those pixels are more like the shape of squares. So this is why we usually don't want to work with rasters where the resolution is in the form of degrees, minutes, seconds, although that's what we have here. Also, there's a dead giveaway here that we're working with a pseudo projection, that for our map layers that we're working with right now in GRASS, that we're working with a pseudo projection rather than a spherical Earth that's been projected onto a two-dimensional surface. So of course the map that we're looking at in GRASS, it looks two-dimensional because it's being displayed to us on our flat screen. But the data is actually stored within the computer in the form of a spherical Earth. And that's why I'm saying that there's this dead giveaway that we're dealing with a pseudo projection. That dead giveaway that we're dealing with a pseudo projection where, while it's being presented to us as two-dimensional, we know that the underlying data is stored in 3 dimensions on a spherical Earth. The dead giveaway of that is that our resolution is in units of minutes, it's in units of degrees, minutes, seconds, and our resolution is at 5 minutes by 5 minutes. The only way that you're going to have your measurement of distance or your resolution in the form of degrees, minutes, seconds is if you're dealing with a pseudo projection where the data is stored on a representation of a spherical Earth and is not actually projected. And we can confirm that by going to Settings, Computational Region, Show Current Region. We see that the projection is listed as 3. So this projection 3, but it says here in parentheses, latitude, longitude. Anytime you see a projection that is latitude, longitude, that means that we are dealing with a pseudo projection where the data is being stored on a spherical Earth in the form of latitudes and longitudes. And we see that our coordinate system is WGS 1984 and that our model for the spheroid shape of the Earth is also WGS 1984, as coordinate systems and ellipsoids tend to go together. Now, I want you to go ahead and click on the Layers tab here to pull up your table of contents, and I want you to show me the resolution for the layer Bio 1. Next, we're going to deal with the spatial extent of our rasters. The rasters we're dealing with right now cover the entire world. That's far too large to work with. It's going to cause all sorts of problems. The area that we're interested for this exercise is the shape of Texas. So we're going to use the shape of Texas from a vector layer as a cookie cutter to make a smaller raster image that only encompasses the state of Texas. We could have used a raster layer cookie cutter as well, but we're going to be using a vector cookie cutter. The first thing we're going to do is make our cookie cutter that we will use to trim this giant raster as well as the other one down to just the state of Texas. We're going to make the spatial extent smaller. Click on File, click on Import Vector Data, and click on Simplified Vector Import with Reprojection. We are choosing this one because our layer has a different, that we're importing, has a different projection and or coordinate system and or ellipsoid from the current GRASS location. So we have to reproject and transform that layer in order to import it into our current GRASS location. Click on Browse. Navigate to the GRASS data folder in your home directory and click on Raster data. Choose cb_2015, etc. .shp. For vector layers, always choose the file ending in .shp. Click on Open. Click on Import. Projection of following layers do not match with layers to be reprojected. What this means is that, as I was telling you, the vector layer that we are importing into this GRASS location has a different projection than the current GRASS location is set up for. Therefore, GRASS is warning us that this layer that we are importing will be reprojected and transformed as needed to make this layer conform to the projection, coordinate system, and ellipsoid that is being used by our current GRASS location. Click Import and Reproject. You can see here with this parentheses showing the date and time that it is finished, so you may now click on Close on the dialog window. I told you earlier that rasters are a map layer, just like vectors of points, lines, and polygons are also a form of map layers. If you look carefully at your screen, you can see that the layer that we just imported of state boundaries is showing up within our database as a map layer on top of the raster layer that we imported earlier. So both raster layers and vector layers can be overlaid on top of one another within the same GIS database. They're both layers, although the data is stored in different formats depending upon whether it's vector data, points, lines, or polygons, or whether it's raster data, these square grid cells. Click on the Layers tab. Right-click on this layer that we just imported of state boundaries. That's if you're on a Windows machine. If you are on a Mac laptop, you will push down on the trackpad with 2 fingers to pull up this drop-down menu. And you will select Show Attribute Data near the bottom. From this attribute data, you will select the state of Texas. With the state of Texas highlighted, you will, on a Windows machine, right-click on the highlighted row. On a Mac laptop, you will push down on the trackpad with 2 fingers on the highlighted row. And you will select Extract Selected Features. We are selecting just the state of Texas from our vector layer of polygons containing all of the different US states. We're going to name this new vector map that we are extracting Texas. Click OK. Now we can close the dialog window. This new layer that we just extracted is not shown on our map because it is not checked. If something's not being shown on your map, one of the things to do is first to see if that layer is showing up in your table of contents. If it is showing up in your table of contents, next thing to do is to check if the checkbox is checked or not. We still can't see the state of Texas as a separate layer because we still have all of the different states being shown in another layer. So we're going to uncheck this layer here, which shows us all of the US states. Now you can see just Texas, and we can also zoom in. So now you can see that we have a layer, and it's a vector layer in the form of a polygon of just the shape of the state of Texas. This will serve as our cookie cutter to clip our 2 raster layers to just encompass the state of Texas. The first step in making our Texas-shaped cookie cutter is to apply something called a raster mask. Click on Raster, click on Mask from the drop-down menu. You have a choice of using a raster as your cookie cutter or using a vector as your cookie cutter. Since, as I already described, our Texas layer is a vector layer made of a polygon, we need to select vector from the list of options for creating a mask. The name of the vector map to use as a mask, if we click on the drop-down menu, we can select Texas. And now we simply select Run. It might seem like we're finished. All of that other raster data is now vanished. And here, I'm going to check this box for our Texas cookie cutter to make it disappear from the map display. And you can see now, and I'm clicking on this layer Bio 12 so that we can see the layer Bio 1 underneath it. I could have also just dragged Bio 1 above Bio 12 to make it show up. But it seems like our job is done because the rest of the raster layer outside of the state of Texas is not showing up in our map display. But we're not done because we still have to export these new raster maps that we have here that are clipped to the state of Texas as new raster layers or as raster data in some other file format that is utilized by a different software program. When exporting our data, we need to pay attention to the size of the grid cells that GRASS GIS is using when we're making our new raster layer. So if the size of the grid cells, if the resolution is very coarse, we'll end up with a very coarse resolution raster layer. It'll be clipped to the state of Texas, but with very coarse resolution. If the size of the grid cells being used by GRASS GIS is very fine-grained, in other words, if the resolution is very fine-grained, then the raster that we make that's clipped to the shape of Texas will be a very fine-grained resolution raster with much more nuanced features and shapes. We set the size of these grid cells by going to Settings, Computational Region, and Setting the Region. So we're going to be setting the resolution here as a part of setting the general regional characteristics of our GRASS location. The first thing we want to do is we want to refer again to our cookie cutter. So we want to set the current region to match our cookie cutter, which is this layer, this vector of the state of Texas. Next, we want to click on this tab for bounds. Click the button Align Region to the resolution. That's just an important step, and if you're troubleshooting why something didn't work, make sure you check this box. This keeps everything aligned properly so that the squares of the grid are aligned over the layer that you're trying to export. Next, click on the tab for resolution. And we're going to use the same resolution of north and south as we have for east and west. So that our resolution is going to be 10 minutes. So every pixel of the grid, every grid cell, in other words, of the grid that GRASS GIS will be using, will be 10 minutes by 10 minutes in size. We're inputting the resolution in the form of degrees:, minutes because distances for this GRASS location are in the form of degrees, minutes, seconds, as I went over with you earlier. So when we specify distances for our resolution, they have to be in terms of degrees, minutes, seconds. So you have to write the degrees colon the minutes. So we want the resolution to be 10 minutes by 10 minutes, so we set the degrees to 0, colon, and then at the minutes marker we set it to 10 minutes. Click on Run. A note, I set the resolution here to 10 minutes. You may be remembering that the resolution of Bio 1 was 5 minutes by 5 minutes. So why did I set it to 10 minutes here? Just to show you that when you export a raster, you can change the resolution if you like, because all you have to do is change the size of the grid that GRASS GIS is using when it exports the raster into a new file or into a new layer. So I was just showing you here that you can change the resolution if you'd like. But even if all we wanted to do was to keep the resolution of our new layer the same at 5 minutes by 5 minutes, you would still have to specify that resolution here. If you didn't, GRASS would pick the size of the grid on its own. And the size of the grid that it were to choose may not be 5 minutes by 5 minutes. It may choose some other arbitrary sized grid. So it's very important when you're working with rasters that you always come in here and specify whatever resolution you want the layers to be when you're making a new layer. So anytime you export something or do any operation on a raster, you want to come here and set the regional settings and specifically set the resolution to whatever you want it to be. Even if you don't want the resolution to change in the new raster that you're making, specify that resolution that you don't want to change here under the regional settings. Okay, we've already run this, so I'm going to close the dialog window. The final step to making our new layer that we can export for use in other programs, for instance, if we wanted to export into the ASCII grid file, a raster file format, which other programs can use, the final step here is to resample our data. And that's a strange term to use because we'll be using this word resampling our raster data even if we're not changing the size of the resolution from the original raster data. You still have to run this resample procedure in order to make your new layer that only includes the state of Texas that can then be exported to other programs. To do this, we go to Raster, Map Type Conversions, Develop Raster Map, Resample using Nearest Neighbor. Here is the layer that we want to make a new layer from, which is clipped just to the state of Texas and contains no other data. We're going to call this new layer Bio 1 Texas, meaning that it's the Bio 1 climatic data only for the state of Texas. And we're going to say resamp so that we can remind ourselves that we've resampled this data to a different resolution. And I'm going to put 10 so we can remember that we've resampled it to 10 minutes by 10 minutes. Here, I'll add a lowercase m so we can remind ourselves it was resampled to 10 minutes. You could call this output layer anything you would like. I'm just using a name that contains information to help us keep track of what we've done. Click on Run. It's finished running, so now click on Close. And here's our new layer, and you can see it still has the checkbox. I'm going to uncheck the other layers so we can just see the layer that we've created. You undoubtedly notice that the colors have changed. This is because this layer is only the state of Texas. So GRASS has changed the color ramp that it used to display the raster data. Whereas before, the color ramp for the entire world for Bio 1, the color ramp was a lot more subtle because of a larger degree of variation in the attributes of the raster across the entire world. Here, because we're just focusing on Texas, there's less variation in the attributes for Bio 1. So GRASS has on its own automatically changed the color ramp that it uses to display the color equivalents of these different raster attributes in the different grid cells to maximize our ability to visually discriminate among the attributes of the different grid cells. We're going to be exporting our clipped rasters into the ASCII grid format, which can be used by other programs, for instance, Maxent for doing ecological niche modeling. But before we do that, we need to double check that our layers are ready to be exported. We need to double check that the new layers that we created really are only for the state of Texas and do not contain any other data. Sometimes with rasters, the other data can still be hiding within this map and just not be displayed because the raster mask is preventing it from being displayed, but that other data could still be there. So it's very common when you're trying to export a raster map like this that you've created, where you thought that it was clipped to the state of Texas, that when you export it, you actually end up exporting a raster map that has the spatial extent of the entire world and data for the entire world, which is not what you intended. The point is, we need to double check that our clipping worked. The way to do that is first to remove our raster mask so that other areas outside of the state of Texas will be displayed on our screen if those other areas still contain data. So come to Raster, come to Mask. Leave everything blank, and under Remove, click the Remove Existing Mask button and click on Run. Now click on Close. And now we can feel assured that we were successful because there's no other raster data that appeared after we removed the raster mask, which means that this layer here only contains raster data for within the state of Texas. We've successfully clipped this layer to the state of Texas. Now, the only thing we have checked here in our table of contents with a check mark is this resampled layer clipped to the state of Texas. Let's uncheck that. Let's go back and look at our original raster layer Bio 1. Now notice that that's not in the shape of Texas. Let's go ahead and right click on it if you're on a Windows machine, or push down on the trackpad with 2 fingers if you're on a Mac laptop, and select Zoom to selected maps. So our original layer still has the spatial extent of the entire world. Nothing happened there. Let's uncheck the box for our original layer, and let's check the box for our clipped layer. It's only our clipped layer, I'm going to zoom into that, which is relegated to just the state of Texas. So that's how we can verify that we've created this layer properly before we move on. Now we're going to export this clipped raster to the ASCII grid file format, which most commonly you would be doing for performing ecological niche modeling. Now, before we do any of that, I need to say, make sure that the only thing that you have checked in your display tab, under your layers tab, the only thing that you have checked should be this one layer our clipped Texas layer that we're going to be exporting to the ASCII grid file format. Everything else should be unchecked. Be sure that you've done that step. Select File, Export Raster Map, and select Common Export Formats. Be sure that the current layer that we're working with is the one that's selected. So it should match what you see in your table of contents. That's what we're exporting. For the name for the output raster file, click on Browse. Navigate to the GRASS data folder in your home directory and have the raster data folder within that GRASS data folder highlighted, but do not double click on it. It should just be highlighted like you see here on my screen. You'll have the green Save button. Click that. Now we choose a name for our file that we are exporting. You can call this file anything that you like as long as it ends in .asc. I'm going to name this file so that it helps me remember the exact data and its resolution and its spatial extent. So I'm going to name this file bio1, just the state of Texas. I'm going to say that I resampled it to 10 minutes, and I'm going to add the file extension .asc. You can call this file anything that you like as long as it ends in the file extension .asc. Now click the green Save button again. Next, before we hit the Run button, we're going to change the raster data format from this drop-down menu. So we're going to open up the drop-down menu and we're going to go to AAI grid. That's the ASCII grid format. And we're still not done. Before we can hit Run, we're going to click on the Creation tab. We're going to click on Do Not Write Non-Standard Metadata. For the data type, we're going to select from the drop-down menu Float64. This allows the attributes in our exported raster file to have decimals. Further down in this dialog window that says Assign a specified no data value to output bands, we're going to type in -9999. In this output file that is created, all of the areas within the spatial extent where there is no data will have the raster attribute -9999, which other programs know to read as meaning that there is no data in that grid cell. And that will allow our raster to have an irregular shape, such as the state of Texas, because the other areas within that square or within that rectangle are coded with the attribute data -9999 in the ASCII grid file. Now we can click on Run. And now that it says it's finished, we can click Close the dialog window. Something else I should have done earlier, I still have this raster mask dialog window open. Go ahead and close that out. Next, we're going to see if we were successful in exporting our raster data for this layer into the ASCII grid file format that can be used by other software programs. Click on File Explorer, which I have pinned to my favorites or which you can find by searching below. Navigate to your home folder and then to your GRASS data folder within your home directory. Click on Raster Data. And here it is, bio1, etc., .asc. That .asc extension shows you that it's the file that we just made. Double click on it. The file has now opened up in a simple text editor because Linux recognized this file as containing simple text data. And this has the exact attributes that we would expect to find in a ASCII grid file, as I described to you earlier. So if your data looks like this, you know that your ASCII grid raster file was exported from GRASS successfully. And we know that this ASCII grid has a resolution of 10 minutes by 10 minutes. And we know that it is only encompassing the state of Texas for the data for the Bio1 attribute from the World Climate Database. Go ahead and close that out. Here's for you to do next. I want you to repeat everything that you just did for Bio 12. So specifically, if you're watching this video on YouTube, I want you to repeat the steps from 39 minutes and 59 seconds into the video until 60 minutes and 45 seconds into the video. I want you to repeat those steps for the Bio 12 layer. If you're watching this on Canvas, I want you to repeat the steps that you see starting at 39 minutes and 30 seconds into the video until 60 minutes and 16 seconds into the video. 39 minutes, 30 seconds until 60 minutes and 16 seconds into the video. That's if you're on Canvas. So repeat those steps for the Bio 12 layer. And be sure that when you repeat those steps, when you're asked to choose a name for a layer and when you're asked to choose a name for a file that you're exporting, be sure to use different names than the names I used in the tutorial the first time around, because now we're exporting a new layer, we're exporting a new file. Those need to have different names the second time around. So do keep that in mind as you're going through the tutorial and doing those steps for the Bio 12 layer. When you're done with that, I want you to make a new cookie cutter in the shape of the state of North Dakota. To do that, if you're watching this video on YouTube, go back to 37 minutes and 29 seconds into the video and follow the steps until 39 minutes and 59 seconds into the video. If you're watching this on Canvas, go back to 37 minutes into the video and follow the steps until 39 minutes and 30 seconds into the video. Now, using that new cookie cutter that's in the shape of North Dakota, not the cookie cutter that's in the shape of Texas, now we're going to be using the cookie cutter in the shape of North Dakota, I want you to repeat the steps where you did everything to exporting those to ASCII raster files in the ASCII grid format. To do that, if you're on YouTube, you'll be following the steps from 39 minutes and 59 seconds in the video until 60 minutes and 45 seconds into the video. If you're on Canvas, you'll be following the steps from 39 minutes and 30 seconds in the video until 60 minutes and 16 seconds in the video. One modification, I want you to make the resolution 20 minutes by 20 minutes as opposed to 10 minutes by 10 minutes. So do those steps using North Dakota as the cookie cutter, end up with your exported ASCII grid files, and go ahead and then open up those ASCII grid files and make sure that they turned out properly. Next, I'm going to show you how to import data from the ASCII grid format into GRASS GIS. Sometimes you may have data in the ASCII grid format that was generated for you by a software program, such as, for instance, MaxSet's output. Or you may have received that data from someone else in the ASCII grid format, and you may wish to manipulate the data within GRASS GIS in some way, change its projection, look at that layer along with other layers. So you may want to bring ASCII grid files into GRASS GIS. So this is how you would do that. We're going to import this raster file that we just made ourselves. This one, bio1 Texas resampled to 10 minutes by 10 minutes.asc. We're going to import that back into GRASS GIS. In reality, you would be using some new ASCII file that some software program generated for you or that someone gave to you. There's no need to re-import an ASCII file that you just generated using GRASS GIS back into GRASS GIS. But we're just going to use that ASCII file because we already have it here. So we're going to utilize it out of convenience. The first thing to do is to stop and think, what is the resolution of the ASCII grid file that I will be importing into GRASS GIS? So remember that the resolution is 10 minutes by 10 minutes. When doing anything with rasters with GRASS GIS, we have to make sure that the grid is set up with the right size cells. So in this case, we need to make sure that our computational region has the right grid cell resolution. Otherwise, when we import our ASCII grid data into GRASS, it'll import that ASCII grid data with the wrong resolution because that ASCII grid data will pass through the wrong size grid cells. So we first need to set our computational region to have the size of the grid cells that we want. In this case, we want to set our computational region to have the size of the grid cells that matches the resolution of the data that we're importing, so that the resolution of the data that we're importing will be maintained, as opposed to having the resolution of that data made blurrier with larger pixel sizes because that data went through a grid with larger grid cells. So we want to have this situation here, not this situation over here, because we want to end up with a raster of Texas like this, not a raster of Texas like this. So we need to set our computational region again. We need to do that now before we try to import our raster. And we need to set our computational region to the resolution of the raster that we are importing. Now, if we double click on the ASCII grid raster that we're importing, the resolution is given here, but it's given here as 0.166 repeating. Now, I told you that the grid size is 10 minutes by 10 minutes. Well, this means the same thing. The ASCII grid format cannot store data as degrees, minutes, seconds. It can only store data as decimal degrees. So this file has converted the resolution from 10 minutes in the degrees, minutes, seconds format into 0.16 degrees in the decimal degrees format. So just be careful about that. The ASCII grid will not show you degrees, minutes, seconds. So you just need to know that the data that you're importing, you need to know its resolution in terms of degrees, minutes, seconds in order to import it into this GRASS location. Now, if we were using a different GRASS location that had units of decimal degrees, then we would be fine. But the units of this GRASS location are degrees, minutes, seconds. So you have to be careful when you're looking at the resolution in the ASCII file. but we know that our resolution is 10 minutes by 10 minutes. So we come here to Settings, Computational Region, Set Region. Now we could set the region to match a vector map. We could set it to match our Texas layer that we originally made as a cookie cutter. But remember that when you import raster data from this ASCII grid format into GRASS GIS, you're not already going to have a cookie cutter. You're going to be importing in some new data. If you do have a cookie cutter already, if you're just importing new data that's already at the extent of the state of Texas and you already have a cookie cutter for the state of Texas, you can set it here. But let's assume that we don't already have a cookie cutter. So we're just going to import the data as is without setting it to match either a vector or a raster. We're going to leave this blank. When we come here to bounds, we're going to align region to resolution. And then when we're going to click on the resolution tab, we're going to set our resolution to 0:10 for 10 minutes by 10 minutes. And we're going to hit run. Now that it's finished, we can click close. And now we're ready to import this file because we've set the resolution of our region. We've set the size of those grid cells to be the size of the grid cells that we want when we pull this data into our GRASS location. So always set your region before you import raster data. Now go to File, Import Raster Data, and choose Import of Common Raster Formats. When you're importing raster data in the form of an ASCII grid, you want to use a GRASS location that's already set up with the projection coordinate system and ellipsoid to match your ASCII raster. When you import your ASCII raster, you need to already have a GRASS location that you're importing it into that has the same projection, coordinate system, and ellipsoid as the ASCII grid file that you're importing. Never try to import an ASCII grid file with reprojection. The GRASS location that we're currently using does match the projection, coordinate system, and ellipsoid of the ASCII raster that we're importing. If not, we would have to create a new GRASS location that matches the specifications of our ASCII grid, and then we would have to import the ASCII grid into that GRASS location instead. Okay, we're going to click on Import of Common Raster Formats. Click on Browse. Navigate to the GRASS directory folder within your home directory and click on Raster Data. Select the Bio1 Texas resampled to 10 minutes by 10 minutes file and click on Open. For the name for the output of this raster map, we're not going to just call it Bio1 Texas resampled to 10 minutes by 10 minutes because we already have that layer in our table of contents. Remember, you wouldn't normally be just re-importing this ASCII file. I'm just doing it because we have that ASCII file handy, and it shows you how to import ASCII files if you get them from some other source. So we're just going to call this layer that we're importing into the table of contents, we'll have it show up in the table of contents as with the name test. Under projection, click override the projection check. We're going to use the current location's projection. Click on run. Since the command is finished, we can click close to close the dialog window. And now let's see if we properly imported it. So I'm just going to move the File Explorer out of the way. I'm going to uncheck all of the boxes except for this new layer called test that we created. And so you can see that we successfully imported the ASCII data as a new raster layer into our GRASS GIS database. And if you imported it correctly, you should have the same resolution that you see here. So the edges should look blocky like my edges here, but they shouldn't be super huge blocks. If they are, then you had your resolution settings wrong when you imported the raster data. So there you go. That should really help you going with rasters. Rasters are more complicated to use in a GIS database as compared to vectors. That's not just true if you use GRASS GIS, that's true if you use ArcGIS, QGIS, any GIS program. Rasters are going to be more complicated. So be very cognizant of all the steps that you took in here when you work with your own raster data in the future.